Hi everyone. In this video we shall be discussing the solutions to the quiz questions of week 3. So most of these questions deal with density matrix and measurements. So let us start with question 1. So the question is, a quantum state is given by psi is equal to 3 by 5 0 plus 4i by 5 1. The corresponding density matrix is given by. To solve this question, we just need to use the definition of a density matrix. So suppose we have a normalized state psi. The density matrix corresponding to this state is given by rho is equal to ket psi multiplied by bra psi. So the given state psi can be represented in the matrix notation by this. One by 5 times 3 and 4i. So the density matrix will be given by this quantity. So the correct answer is option B. Now let us check the next question. The next question is, consider the density matrix corresponding to the state 0 0 plus 0 1 plus 1 1 upon root 3, of which the first qubit is with Alice and the second with Bob. The reduced density matrix for Alice is given by what? So let us write down the given state, which we shall call psi, which is given by 0 0 plus 0 1 plus 1 1 upon root 3, where the first number corresponds to the qubit that Alice has and the second number corresponds to the bit that Bob has. This is a simple representation of this. So the density matrix corresponding to this would just be ket psi times bra psi, which would be now what we need is the reduced density matrix for Alice. So a reduced density matrix for one qubit is the same as the trace of the density matrix with respect to the second bit. Hence, what we need to find out is this. Now this can be easily found out. So using the equation from last slide, if we take 0, if we multiply bra 0 on this side, the only term which will be left will be the first term. And if we multiply by ket 0 from the right side, only this bit will be left. So the first term would only give 0a 0a upon 3. Now for the second term, notice that two of these terms, two of the kets have 1 in B's qubit. So both of these terms will remain, and when we multiply by 1 by ket 1 B from the right side, these two terms will remain. Hence the second term would give this quantity. So we can simplify this and write this in the matrix form. So 0a, 0a has the coefficient 1 by 3 plus 1 by 3, which is 2 by 3. Then 0, 1, the state 0, 1 has coefficient 1 by 3. 1, 1 has the coefficient 1 by 3, and 1, 0 also has the coefficient 1 by 3. So all the other terms in the matrix will have 1 by 3 as the coefficient. So in matrix form, what we have is 1 by 3. 0, 0 would go in the 1, 1 place. So we have 2 here and 1 in every other place. So coming back to the options, option B is the one which we have gotten. So option B is correct. Now in question 3, a matrix has been given to us and it has been claimed that this matrix represents a density matrix. So what we need to find out is whether this matrix really does represent a density matrix, and if it is, then whether it corresponds to a pure state or a mixed state. So the given matrix is 1 by 4 times 2, 1, 1. Now the first thing to check, now the first condition that needs to be checked whenever a claim is made regarding a matrix being a density matrix is to check whether the trace is 1. So the trace of the given matrix is not equal to 1. It's 3 by 4. Hence, it is not a density matrix, because every density matrix has to satisfy the condition that its trace has to be 1. So the correct answer is option C, which is that rho is not a valid density matrix. Now question 4 is, for mixed states considering the Bloch sphere, the distance from the center is equal to 1, more than 1, less than 1, or 0. So this was discussed extensively in the lectures and as well as in the lecture notes. A pure state always corresponds to a point on the Bloch sphere, and any point on the Bloch sphere corresponds uniquely to one and only one pure state. On the other hand, a mixed state corresponds to a point which lies inside a Bloch sphere. Hence, its distance from the origin is less than 1. So the correct answer is option C. In question 5, we have been given a mixture of states, with 75% of the states being in the state plus and the remaining 25% being in the state minus. We have to find the probability that a measurement on this mixture will give us the state 0. So the first step here would be to find out the density matrix corresponding to this mixture, and then we have to find out the 0, 0 element of this matrix. So let us first calculate the density matrix. So the density matrix is given by summation over I, state I times Fi, where Fi is the fraction of the states which are in the state I. So in this case we only have states plus and minus, and this summation boils down to this value. Now we can convert this directly into matrix form in the computational basis. So this would be 3 by 4 times 1 upon root 2, 1, 1, which is ket plus this multiplied by bra plus 1 upon 4 times 1 upon root 2, 1 minus 1, which is ket minus times 1 upon root 2, 1 minus 1, which is bra minus. On simplifying, this comes out to be 3 by 16 times 1 plus 1 by 16 times 1 minus 1 minus 1, 1. Now all we need is the 1, 1 element of this matrix. That is, we want this quantity. So this is just the row 1, column 1 element of the row matrix. So the first element of the matrix is 3 by 16 plus 1 by 16. sorry, this has to be 8. So the first element is 3 by 8 plus 1 by 8, which is equal to 4 by 8, which is 1 by 2. So the correct answer is option B, which is 1 by 2. The next question is, in the above problem, the density matrix of the system after the measurement is what? So clearly after measuring, the state which we have is the state 0, which is a pure state, and the density matrix corresponding to this is trivially ket psi bra psi, which is 0, 0. Hence the correct answer is option C. The next question is, a qtrit is like a qubit, but a qtrit can be in 3 states. So till now we have been dealing with quantum states which can only be in 2 states, either 0 or 1. But in this question we have a 3-state system. So we have a state plus, a state 0, and a state minus. And it has been given that they are respectively the eigenstates of angular momentum operator J is equal to 1, with eigenvalues Jz equal to plus 1, 0, and minus 1. Given the density matrix this, the average value Jz is what? And we also want to find out the standard deviation for this. So the density matrix given is this. Now as discussed in the lectures, we know that the expectation value of any operator, suppose operator A, then the expectation value of operator A is given by the trace of rho A, which is the same as the trace of A rho. So here we have to find out the average value of Jz. Now if we just need to replace A with Jz. So Jz expectation value would be trace of Jz times rho, and Jz is given by 1 0 0 0 0 0 0 0 minus 1. The reason why it is this is because if we are writing Jz in its eigenbasis, then only the diagonal elements are non-zero and all the off-diagonal elements are 0. And the diagonal elements are the eigenvalues corresponding to this operator. So the eigenvalues of Jz have already been given to be 1, 0, and minus 1. Hence, the diagonal elements are these and off-diagonal elements are 0. So we can easily calculate the expectation value of Jz now. It is the trace of 1 0 0 0 0 0 0 0 minus 1 times rho, which is 1 by 4 times 2 1 1 1 1 1 0 1 0 1. Now this is an easy evaluation which comes out to be 1 by 4. The next part of the question is, what is the standard deviation? And the standard deviation is given by this. Now we have already calculated this quantity. All we need to do is calculate this quantity. Again, this is just another operator. So we have expectation value of Jz square equal to trace of Jz square times rho. Both rho and Jz have been provided, and this simple calculation gives the answer root 11 by 4. So the correct answer is option A. Question 8 is about POVMs. We have been given two states which are, let us name them psi 1 and psi 2. So state psi 1 is 1 and state psi 2 is given to be 1 upon root 2 times 0 plus 1. So the question asks, a POVM that allows imperfect identification of the states 1 and 0 plus 1 by root 2 is given by, and we have been provided with 4 options. Each of them is a set of POVMs. So what we need to find out is which of these POVMs will help in definite identification of either of these states. So as discussed in the lecture, suppose we have these 3 operators in the POVM. Then what we require is that the expectation value of E1 with respect to psi1 be equal to 0 or some positive quantity. But if it is 0, then the expectation value of E1 with respect to psi2 should be a positive quantity, and if it is positive, then this one should be 0. So one of these operators should give an expectation value of 0 with psi1 or psi2 and give a positive value for the other one, and the same should hold true for E2, except that now the expectation values would be flipped. But the third operator will not give us will always give non-zero values. So all we need to do is to check whether this happens. This happens for both E1 and E2. So let us directly check the correct answer, which is option A. So option A gives E1 equal to 0. Now the expectation value of E1 with respect to psi1 is clearly 0, because this would be root 2 upon root 2 plus 1 times 1 0 plus 0 1, which is 0. And the expectation value of E1 with respect to psi2 should turn out to be non-zero. So that quantity is now simplifying from the last page. What we have is so the 0 0 will give a constant and 0 0 will give one constant, and these terms they will give 0. So what we have is 1 upon root 2 times root 2 upon root 2 plus 1 times 1 upon root 2, which is clearly some quantity which is not 0. So E1 clearly is able to distinguish between psi1 and psi2. As for E2, the expectation value of E2 with respect to psi2 is equal to 0. This you can notice by realizing that 0 plus 1 upon root 2, 0 minus 1 upon root 2 is perpendicular to 0 plus 1 upon root 2. So this is 0, and on calculating the expectation value with respect to 1, this is psi1, this will turn out to be the same quantity. So E1 and E2 are clearly able to distinguish between psi1 and psi2. So option A is correct. If you calculate the expectation values of E1 and E2 with respect to psi1 and psi2, you will find out for each of the other options that this is not satisfied. None of them would give the expectation value for 1 0 and expectation value for the other state to be a positive quantity. So the correct answer is option A. Now question 9 is, which of the following properties must be satisfied by a density matrix? Now a density matrix is always Hermitian. So consider the density matrix for a pure state, which would be just given by this. If ket psi represents the state, then rho dagger is again psi psi, which is same as rho. hence it is Hermitian. It can also be checked for mixed states. So suppose we have a mixed state and we have density matrix given by this expression. Then again, if we take the dagger of this, then since pi is a real quantity, pi star will just be equal to pi. So again we get rho again. So rho is again Hermitian. So the first option is correct. Also, as discussed in the lecture, the trace is also equal to 1 and it is also a positive matrix. So the correct answers are options A, C and D. Now the question 10 is, which of the following properties must be satisfied by the density matrix for a mixed state? So option A is definitely correct, because the trace of any density matrix has to be equal to 1, irrespective of whether it's pure or whether it corresponds to a pure state or a mixed state. So option A is correct. The second option is the trace of the square of the matrix should be less than 1. This is a property which helps us distinguish between a pure state and a mixed state, because the trace of the square of a density matrix is always equal to 1 for a pure state and it is less than 1 for a mixed state. So option B is also correct. Option C is its eigenvalues must be non-negative. This in fact is true for every density matrix, irrespective of whether it corresponds to a mixed state or a pure state. So option C is also correct. Option D again is, as we discussed before, it says that the expectation value of any operator A is given by trace of A rho, which is also true. So all the options are correct for this question. Now question 11 is, which of the following properties must be satisfied for a pure state density matrix? So options A, B and C are correct. Let's go through each of them one by one. So the first one is rho is equal to rho square. So for a pure state psi, which is normalized, the density matrix is given by this quantity. Therefore rho square would just be ket psi, bra psi, ket psi, bra psi. Since we have already assumed that the state psi is normalized, this is equal to 1 and we get back ket psi, bra psi again, which is clearly rho. Hence option A is correct. Now option B talks about the number of non-zero eigenvalues of the density matrix for a pure state. So as we will see, this is indeed true. It has only one non-zero eigenvalue. To realize this, let's assume that a ket A is an eigenstate of the density operator rho. So what we have is rho times A is equal to A times A, where A is the eigenvalue corresponding to this state. So if we multiply again by rho on both sides, we get rho square of A is equal to A rho A. Now rho square, as we saw before, is equal to rho. So rho times A is equal to A times rho of A. But rho of A is equal to A times A. So we get A square A. So if we compare equations 1 and 2, what we get is that A is equal to A square for non-trivial states A. So either A can be 0 or A is equal to 1. So now using the property that the trace of any density matrix has to be equal to 1, and using the fact that A's are only zeros or ones, that is the eigenvalues are only zeros and ones, we can conclude that there's exactly one non-zero eigenvalue. This is because the trace of any matrix is given by the sum of its eigenvalues. So if lambda I is an eigenvalue of rho, then the trace of rho will be given by the sum of the eigenvalues of rho. So clearly, if the sum of all eigenvalues of the given of a pure state density matrix is 1, then this means only one eigenvalue is 1 and all other eigenvalues are 0, since these are the only allowed eigenvalues. Hence option B is correct. Let's come to option C. Option C gives us an equation which is that rho mn times rho nm is equal to rho mm times rho nn. We need to check if this is correct. Now let us look at the left hand side. The left hand side is rho mn times rho nm. So this can be given by, this is equal to m rho n times n rho m, where m and n are the basis states or the states of the matrix. So since we have to use the fact that this is a pure state, so we can write rho as ket psi bra psi. If we put this, what we get is, if we substitute this in both these, what we get is m psi psi n if we just rearrange this, sorry, this is m. If we just rearrange this and group these two together and these two together, what we get is now clearly this is rho and m rho m is the mth element, while this thing, the other quantity is rho n comma n. So clearly this is equal to the RHS. So option C is also correct. Now option D states that the density matrix should be unitary, but there is no reason for it to be unitary, hence option D is not necessarily true. Question 12 is, we have been given a matrix and we have to check whether each of these is true or false. So we have rho equal to 0 0, sorry, sigma equal to 0 0 plus 1 1 upon 2. So the first option is trace of rho is equal to 0, trace of rho is equal to 1. So in matrix form, this is same as half 1 0 0 1. Clearly the trace of sigma is equal to 1. So option A is correct. Now option B is that trace of sigma square is equal to 1. If you evaluate sigma square, it will turn out that its trace is not equal to 1. So option B is incorrect. Now option C is that, option C states rho is a pure state. But in this case, we can easily see that this should correspond to a mixed state, because we can write rho as 1 by 2 times 0 0 plus 1 by 2 1 1. So this should correspond to a mixture where half of the fraction of half of the states are in state 1, sorry, state 0, and 50% of the states are in 50% of the ensemble is in state 1. So just by looking at this equation, we can guess that they should correspond to a mixed state. But to clearly identify this, we can use another fact, which is that for a pure state, trace of sigma square has to be equal to 1. But this is not true. Hence, this has to correspond to, since this is not true, it has to correspond to a mixed state. So option D is correct. So options A and D are the right answer. Now question 13 is, the density matrix of a system is given by some matrix. So the matrix which is given to us is 1 by 5 times 1, 2, 2, 4. To first check whether this is in fact a density matrix, we need to check whether this is true, whether the trace of rho is equal to 1. And as we can see, the trace of rho is indeed 1. Now to distinguish between a pure and a mixed state, what we do is to check the trace of rho square. If the trace of rho square is equal to 1, then this is a pure state. But if the trace is less than 1, then this corresponds to a mixed state. So we need to find out the trace of rho square. So rho square is equal to 1 by 5, 2 by 5, 2 by 5, 4 by 5 times 1 by 5, 2 by 5. So for the trace, we only need to consider the 1, 1 and 2, 2 element. So the 1, 1 element is 1 by 25 times 4 by 25, which is 5 by 25, plus the other diagonal element is 4 by 25 plus 16 by 25, which is equal to 1. So the trace, so this is correct. So the given density matrix corresponds to a pure state. So option A is correct. Now option B, of course, is incorrect because it states that it is a mixed state. Option C is, the probability that a measurement of the system will find it in state 0 is 1 by 5. So now realize that the probability of finding a pure state or a mixed state in any state, suppose say state phi, is given by the expectation value of rho with respect to phi. So in this case, instead of in place of phi, we have the state 0. So what we need is 0, rho, 0, which is just the 1, 1 element of the matrix. Which is equal to 1 by 5. So option C is correct. Option D is, the expectation value of sigma x in this state is 4 by 5. So as we have checked previously, the expectation value of any operator is just the trace of the product of that operator with the density matrix. Hence, we have the expectation value of sigma x is equal to the trace of sigma x times rho, which is equal to the trace of sigma x is 0, 1, 1, 0, and rho has been given to be 1 by 5 times 1, 2, 2, 4. So this is, so the first element is 2 by 5, and the second element, the second diagonal element is 0 into 2 plus 4 into 0 upon 5, which is 2 by 5. So the expectation value of sigma x is indeed 4 by 5. So option D is also correct. So the correct answers are options A, C, and D. Now coming to the last question. The question states, it was shown that the reduced density matrix of a 2-qubit state gives a mixed state. The converse of this is also true. That is, given a reduced density matrix for a single qubit, one can construct a 2-qubit pure state whose partial trace would produce the given density matrix. This is known as purification. So given a density matrix rho, a purification is given by which of these? So we have been given a reduced density matrix, and what we want to find out is which of the given states in options A, B, C, and D which of these on reduction would give the given row. So the given density matrix rho is 1 upon 4, 1, 0, 0, 3. What we need to find out is a state psi of which this row is a reduced density matrix. So let us check option B. Let us check the correct options directly. So option B is that psi is given by 1 upon 2, 1, 0 times 1, 0 plus root 3 times 0, 1, 0, 1. If we write this in, if we expand this in ket notation, we would get 1 upon 2 times 1a, 0a, 0b plus root 3, 1a, 1b. So the density matrix rho AB would be given by ket rho bra rho, which would be 1 by 4 times 0, 0 plus root 3, 1, 1 times 0, 0 plus root 3, 1, 1. Now we need to check that, now we need to take the reduced density matrix of this, that is we need to take the trace of rho AB with respect to B. And if this turns out to be the same as rho, then then this state should correspond to a right answer. So trace along B of rho AB is given by which is, so taking the 0, so taking this value, what we would get the product of only these two elements, and for this quantity we would get the product of only these two elements. So what we would get is 1 by 4 times 0, 0 plus 3 by 4 times 1, 1, of course for the state A. And in matrix representation, this turns out to be 1, 0, 0, 3, which is same as the row which was given to us. So option B is correct. Now similarly, if you try out this procedure for options A, C and D, it turns out that only options B and D give row on reduction. So options B and D are correct.